Some numbers stand out, others just blend in, but how can we tell which data points are truly unusual? This question, how unusual is an outcome, is at the heart of statistical analysis. When working with normal distributions, z-scores give us a way to measure how far a value strays from the average, thus telling us how likely or unlikely it was to get that outcome. Here we have a normal distribution with a mean of 52 and a standard deviation of 24. Notice the mean 52 is in the middle, and the axis was scaled so that we go out by 1, 2, and 3 standard deviations from the mean. So we're adding 24 each time because that's the standard deviation. And then over here, we're subtracting 24 each time. Encountering a data point like 62 would not be unusual at all because there are lots of other data points near the mean. Even getting a 20 would not seem strange, even though it's less likely than getting a 62. But 130? Not impossible, but very, very unlikely, and by most measures could be called an outlier. There are different ways to locate outliers depending on the situation, but one way would be to say that any data point more than 3 standard deviations away from the mean should be called an outlier. So an example of a low outlier in this distribution would be something smaller than negative 20, like negative 23. And a high outlier would be some number greater than 124. So we'll just say 130. These are examples of outliers because they are more than 3 standard deviations away from the mean. We can calculate what is called a z-score that will tell us how many standard deviations away from the mean a data point is, thus telling us how likely or unlikely that result was. Remember, data points more than 3 standard deviations from the mean are very unusual. Now, to calculate z, which remember tells us how many standard deviations away from the mean that data point is, first we subtract the mean from the data point, and we divide by the standard deviation. The numerator of the formula tells us how far the data point is from the mean, and then by dividing by the standard deviation, it tells us how many standard deviations that distance is. So once again, the z-score tells us how many standard deviations away from the mean the data point is. So for this one, z equals the x minus the mean of the population divided by the standard deviation of the population. So 31 minus 32, that's negative 1. And we can turn this fraction into a division problem. Negative 1 divided by 3 equals negative 0.333, and so on. Let's round to the nearest hundredths place. So this data point of 31 is less than 1 standard deviation below the mean, which would indicate it is nowhere near being an outlier. Let's calculate z again. The grades on a history exam were roughly normally distributed with an average of 74 and a standard deviation of 6. Grady scored a 77 on the exam. Find the z-score for Grady's score. Round to 2 decimal places if necessary. So by calculating the z-score, we're going to figure out how many standard deviations away from the mean that Grady is. And his score was above the average, so that means we should get a positive z. Okay, so z equals the x, or the data point, minus the mean mu divided by the standard deviation sigma. All right, his score was 77. The mean is 74. And the standard deviation is 6. 77 minus 74, that's 3. And 3 divided by 6 is 0.5. So his test score is 0.5 standard deviations above the mean, or half a standard deviation above the mean. Once again, nowhere near being an outlier, because this would need to be above 3 to be considered an outlier. So let's make sure we understand this idea that z-scores tell us how many standard deviations above or below the mean a data point is. So we have 3 z-scores that were calculated for 3 different data points, and we're wondering which data point is farthest from the mean. Okay, so x has a z-score of 2.09, y 1.24, and z negative 0.34. So the data point that's furthest from the mean will be x. So x is more than 2 standard deviations above the mean, y is a little bit more than 1 standard deviation above the mean, and z is just a little bit below the mean, but less than 1 standard deviation away from the mean. We're going to switch things up a little bit here. We're going to find x, or the data point, given the z-score. So if Natalie wants her race time once around the track to be 3 standard deviations below the mean, so remember, when you're running a race, you want your times to be smaller, or which would be faster. What does her time need to be if the mean time for her class was 92 seconds and the standard deviation was 10 seconds? All right, let's just jot down that information. The mean is 92 and the standard deviation is 10. All right, so to calculate z, it's the data point x minus the mean over the standard deviation. Now, in this case, she wants her time to be 3 standard deviations below the mean. So the z is negative 3. And she doesn't know what her time is, what time she needs. So we want to solve for x. We know the mean is 92. And the standard deviation is 10. All right, solving for x, the first thing we could do is multiply both sides by 10 to get rid of this denominator. So let's see, that would be, negative 3 times 10, that's negative 30. And then we've got x minus 92 on the right. So all I did there is multiply both sides by 10. Now to get x by itself, we'll add 92. And negative 30 plus 92, that is 62. So that tells us that she needs to run around the track in 62 seconds in order to be 3 standard deviations below the mean. Okay, here we're going to do something interesting with z-scores. We're going to compare 2 outcomes from different populations. So here we have the average time for 10th graders and the standard deviation for that, and the average time for 11th graders and their standard deviation. So these are 2 different groups of people, 10th graders and 11th graders. Notice the 11th graders ran around the track faster on average than the 10th graders. So Joyce, a 10th grader, she ran around the track in 81 seconds. And Alexa, an 11th grader, she ran around the track in 79 seconds, faster. But who ran faster relative to their grade level? All right, so 11th graders are in general faster than 10th graders. So we're wondering which of these 2 times is faster relative to their grade level. All right, so let's figure out their 2 z-scores. All right, let's calculate Joyce's z-score. So her z will equal her time minus the mean for the 10th graders, and all that divided by the standard deviation for the 10th graders. All right, 81 minus 95, that's negative 14. And then we divide that by 12 and get negative 1.167. So she's a little bit more than 1 standard deviation below the mean. All right, let's calculate Alexa's z-score. All right, she ran the lap in 79 seconds. The mean for 11th graders is 89 seconds. We'll divide that by the standard deviation. Right, 79 minus 89 is negative 10. And negative 10 divided by 8 is negative 1.25. Now, since this was a race and we wanted to be below the mean, so Alexa's time was faster relative to her grade level because she was further below the mean than Joyce was. I hope these examples about calculating z-scores to see how many standard deviations above or below the mean a data point is have been helpful. This is Mr. Ela, signing off.